Hello, everyone, and welcome to this Nordic Tech webinar. The topic for today's webinar is, as you can see, developing Bluetooth mesh products. Introduction. My name is Robin Soltnes. I am a product marketing engineer here at Nordic Semiconductor. I will be working behind the scenes on today's webinar. Together with me, I have Omkar Kulkarni, a senior R&D engineer also at Nordic Semiconductor, who will be doing the main part of the presenting in this webinar. And we've also enlisted the help of Terje Schilderup, an application engineer also here in Nordic Semiconductor, who will help answering questions in the Q&A at the end. But first, I'll go through some practicalities. And the duration of this webinar is about 60 minutes total, consisting of a 45-minute presentation and 15 minutes for Q&A. We encourage everyone to ask questions. Please type them in the top right-hand sidebar. All questions are kept anonymous, and we ask that you try to keep this relevant to the topic of today's webinar. And we will answer them towards the end. The chat on the bottom right-hand sidebar is not anonymous, and we want to discourage you from using this for questions because it's very hard for us to monitor when we're doing live presentations as it zooms by. If your question isn't answered, or if you have more questions or questions that are so long that or they require such long answers that you would need a personal help, you can go to devzone.nordicsemi.com and have a application engineer in tech support help you out personally and directly. After the completion of this webinar, we will post a recording together with the presentation slides at the webinars.nordicsemi.com. And with that, I hand the word over to you, Omkar.
Thank you. Hello everyone. In today's webinar, we will do a quick recap of Bluetooth Mesh. Then we will take a look at some of the concepts around Bluetooth Mesh products. Then we will do a code walkthrough for the light and switch samples from RF Connect SDK. And towards the end, we will understand some more mesh networking concept while seeing a demonstration for a mini mesh network. I hope this introductory webinar will help you in getting started with Bluetooth Mesh product development. Let's do a quick recap of Bluetooth Mesh. What is the Bluetooth Mesh? It is a short-range wireless networking technology using Bluetooth Low Energy Protocol as its bearer layer. Mesh packets are encapsulated in BLE advertisements or GATT packets. Mesh networking helps to extend the range of communication for normal BLE devices through something called as managed flooding approach. In this, some of the nodes in the network act as relay nodes. They relay the packets they receive, thereby increasing the range of communication. This way, several nodes in the network can communicate with one another or with the nodes that are further away from them. Let's look at some of the important terminology that we will use throughout this presentation. An unprovisioned device is a device that can be provisioned into a Bluetooth mesh network. A process of adding an unprovisioned device to a network is called as provisioning. Once the device gets provisioned, it is called as a node in a mesh network. A device that is capable of performing provisioning is called as a provisioner. A node that is a provisioner and has the capability to configure other mesh nodes is called as network configuration manager. Typically a phone or a tablet. An addressable entity within a device is called as an element. With this, let's dive into the layered architecture of Bluetooth Mesh. Bluetooth Mesh protocol is composed of several layers. At its base is a Bluetooth Low Energy Core specification, and at the top is a model layer. The model layer represents application layer. It contains server and client models. The server model holds the state and executes defined behavior. The client model communicates with the peer server to get or set the state values or to cause an action. These models are identified by model IDs. It is not necessarily that all the functionality in the model layer is split into server or client model components. There can be hybrid vendor models which act simultaneously as clients and servers. A foundation model layer handles the node configuration. Below this are the mesh networking layers, namely access layer, upper transport layer, lower transport layer, a network layer, and a bearer layer. These networking stack layers implement the mesh networking. Model layer is primarily defined in the Bluetooth mesh model specification. This specification standardizes typical user application scenarios with a defined set of mesh models. Vendors can implement their own models to enhance the functionality of the existing Bluetooth mesh models or add their own new functionality. For example, a generic on-off client model defined in Bluetooth mesh model specification can represent a switch device. Similarly, a generic on-off server model can represent a light bulb. And when these two models are used together, they can form a usable system, a light switch and a light bulb. Let's briefly take a look at the models and their architecture. Server models hold the states, and client models set or query the state values using set of model messages. Change of state causes an action on the server models. Some of the server model states can also be bound to one another, meaning when the state value of one server model changes, it can influence the state value of another server model on the same device. Foundation models are crucial for configuring the node settings. They are at the heart of the setting and parameter control. There are two foundation models defined in the mesh profile specification. They are config server and peer client model, a health server and a peer client model. Config server is used to configure subscription publication, heartbeat settings, or other node features, as well as to add or remove keys from the node or execute security procedures. Health model is especially useful for fault monitoring and attention timer application. The attention timer available in the health model can be used to seek attention from the user when needed. Okay, now let's take a look at some of the concepts around Bluetooth mesh product. What constitutes a mesh product? Well, a Bluetooth mesh product is a device that can be provisioned by any available provisioner on the market. Once provisioned, it performs certain functionality in a mesh network. For example, this product can act as a relay, it can act as a light fixture or a switch, or a protocol translator, or a proxy device, or a friend, etc. How provisioner views the devices on the mesh network. All mesh nodes convey their functionality through a device composition data page 0 state. After device is provisioned, Network Configuration Manager reads CDP0 to understand what the devices can do. The device composition data page 0 contains information about various models present on the device, their order, the feature set of the device, vendor identifier, company identifier, and the product identifier. Okay, how do you create different kinds of mesh devices? Well, the presence of models on a device loosely identify the device functionality. Bluetooth mesh model specification provides many models for most common functionalities for network lighting control applications. Of course, mesh models can be used for non-lighting applications as well, for example, controlling window blinds or ceiling fans. But we will concentrate on lighting applications. Devices can instantiate several models for implementing the complex functionality. Some examples would be as follows. Let's say a device has a generic on-off client. Then such a device potentially would represent on-off switch. If it has on-off server, it could represent a simple light fixture. If the device contains light LC server and corresponding models, then it is a complex light fixture with timeouts and sensor-driven control. If the device has HSL server, it can be considered as colored light. If it has CTL server, then it's a light with a color temperature control. Similarly, if it has a generic sensor server, then it can be considered as a sensor device. Network Configuration Manager can infer the device types using various methods. The first and foremost is device composition page 0. Most commonly used device types can be inferred using this information. There can be another method of inferring device type, such as out-of-band association of the device UID with a specific type of device, or a combination of both. For example, your vendor ecosystem can provide a way to associate a device UID with certain kind of device type by fetching some information from the cloud. Or you could combine this approach with the device composition data page 0 and provide rich GUI interface. Let's look at this device composition and what it is. Element is the addressable entity on a node. A single element on a node can contain one or more model instances. However, a single model cannot be instantiated twice on the same element. Certain models can have associated models on several elements. This can be used by Network Configuration Manager to inform users about what the device does, and it can also help in populating the GUI elements. Let's look at the simplistic mesh lighting system. A mesh lighting system would contain a switch node and a light node. A switch node may be represented by creating a device with generic on-off client, and a light node may be represented by a device containing generic on-off server. A client would then use get set messages to get or set the values on the server, and the server would respond its value using status messages. The light device would typically contain a light emitting component or interface to such a component, for example, a driver. And it will also have a communication component to receive commands and generate output signals. Typically, this communication component is the place where Bluetooth stack and the Bluetooth mesh stack would be implemented. A switch device similarly would have a button interface and also RF communication interface. With these basics, now let's move our attention to the NRF Connect SDK samples. We will take a look at light and switch samples from NRF Connect SDK and understand how these samples are architected and structured. NRF Connect SDK is based on Zephyr real-time operating system. It provides Nordic soft device controller along with Zephyr Bluetooth mesh stack and Nordic implementation of Bluetooth mesh models. It also has various peripheral drivers and libraries that can be used for user applications. You can navigate to NRF Connect SDK portal and look for the Bluetooth samples. In that, you would find Bluetooth mesh samples towards the end of the list. Let's dive into a light switch sample. The light switch sample in NRF Connect SDK is based on generic on-off client model. It represents a multi-switch device that can control up to 4 light fixtures using a same device. The main model representing this functionality is on-off client. 4 instances on 4 elements represent 4 buttons on the DKs. Some of the development kits have less number of buttons, and as we will see shortly, that the conditional compilation will instantiate one or more instances of the generic on-off client model. In today's demo, we will use NRF53DK to represent the light switch. This DK has 4 buttons, so we will use all 4 instances. Let's look at the code organization of mesh samples. This is common for all of them. The mesh samples mainly have 2 modules. First one is main.c, which initializes Bluetooth subsystem, mesh, and hardware. And the second one is model handler.c, that contains Bluetooth mesh specific code, device composition, and model handlers. Some of the samples may have additional modules required for sample specific functionality. Let's jump into the light switch sample. I'm launching VS Code. Okay, I'm going to navigate to the samples directory, Bluetooth, mesh, and a light switch sample. So in this, let's open the source and main.c module. As mentioned before, main.c is used to initialize the Bluetooth subsystem. It is done by calling BT enable API, which accepts BT ready as the callback input. This callback is called once the Bluetooth subsystem is completely initialized. Either successfully or unsuccessfully, you will get this information in the parameter of the callback. Once the Bluetooth subsystem is initialized successfully, the sample will initialize LEDs on the DKs and then the buttons and eventually mesh subsystem. For the mesh subsystem initialization, it requires node provisioning information and node composition information. This is obtained by BT-mesh DK-prov init API and model handler init API. DK-prov init API provides a generic provisioning context suitable for most applications. Model handler init API provides the composition context. And this is defined in the model handler.c. After that, settings are loaded and BT Mesh Pro enable API is called to start advertising unprovisioned device beacon. After this, the sample is ready for operation. Now let's jump to model handler and see how it is structured. As mentioned few moments before, model handler init callback prepares the device composition and returns it to be used for mesh subsystem initialization. It adds handlers for the decay buttons and initializes a delayable work item. Now let's see how the composition of the device is constructed. It is done using a data structure called as BT Mesh Comp. A BT Mesh Comp is an elaborate data structure that requires company ID, product ID, and vendor identifier, the number of elements available on the device, and pointer to the list of elements. In this sample, only company identifier is initialized with the Nordic ID, and other identifiers are skipped. They get the default value of 0. The elements on the device are defined using a separate structure which contains array of individual elements. As you can see here, there are several conditional compilations. Since this is a switch example, depending on whether the board has a particular switch instance or not, it will include the additional elements. If board has all 4 switches, all 4 elements will be instantiated. BT mesh element is a helper macro to define a mesh element within an array. As you can see here, the code also uses another helper macro, BT mesh model list, to list all the applicable models on the element. Config server and health server are mandatory foundation models, and they must reside on the first element. Therefore, they are listed here. After that, on-off client is instantiated, and as you can see on remaining 3 elements, there is only one model, that is on-off client. The on-off client instantiation requires a context structure. Since this sample provides up to 4 instances of on-off client, their context structures are defined in the buttons array. Here you can see that buttons array contains 4 instances of BT mesh on-off client. Each one of these instances require a status handler. In this sample, status handler is common for all the instances. You can use either the common status handler or you can use separate handlers. Generally, for the same type of client or server model instances, a same status handler is used. And within the status handler, you can look at the client pointer to resolve the correct model instance if needed. Within the status handler, it receives on-off status message, and the sample will print the values received in the status response. It will also set the LED on decay to provide a visual indication of the received value. All right. Then let's look at what happens when user presses the button. This is handled by the button handler callback. The button handler callback only responds if Bluetooth mesh device is provisioned. Otherwise, it doesn't do anything. It iterates through all the 4 buttons and checks which button has changed its state. Depending on which button is pressed, it will select the correct client instance and trigger BT mesh on-off client set command. If the publish address is unicast, then an acknowledged set API will be used. If the publish address is not a unicast address, that means it is a group address or a virtual address, then it will use unacknowledged equivalent of the on-off set API. There is one additional part that I must mention here, the health server and its callbacks. As I mentioned before, health server is a foundation model. It is mandatory to have one. The health server requires 2 callbacks defined in the application, the attention on and attention off callback. So when health server receives a message to turn on the attention on callback is called, and after a given amount of time expires, attention off callback is called. So these callbacks are used to blink LEDs on the board to attract the user attention. In your product, you could use this attention callback mechanism to attract the attention of the user. This is really important. Imagine if you have a bunch of mesh lights on your desk and you want to provision them. It will be impossible to determine which light you are provisioning if there is no visual indication on those lights. The attention callback helps to do exactly that. During the demo, we will see how it helps. This is the overview of light switch sample. And now let us jump to the light sample. Okay, now let's take a look at the light sample. It is a simple light representing two states of operation, either on or off. And the main model which represents this functionality is generic on-off server. The sample has 4 instances of generic on-off server on 4 different elements, and they are conditionally present depending on the availability of LEDs on a chosen DK. We will run this sample on Thingy 53, and Thingy 53 has 3 LEDs on it. Therefore, this sample will instantiate 3 elements and put generic on-off servers on them. In actual demonstration though, we will be only using 1 LED out of these 3 for simplicity. Let's take a look at the code for the light sample. For this code walkthrough, we will be using an RF Connect SDK extension to also give you an idea how you can do the development using an RF Connect SDK extension in VS Code. So let's add the application. I'm navigating to the samples directory. So first thing we need to do is to add the build configuration. Let's click on the build configuration addition option. We will select Thingy 53 CPU app configuration as the mesh stack, and the application will reside in the application core of NRF 53. We will also select project conf in the sample directory as the configuration file, and we don't want to build it right now. So we will uncheck build after generating configuration box. After that, I click on generate configuration to generate the build config, and then we will be able to browse the source code. All right, so we can see the light sample code here now. We have the main.c file here. As I mentioned before, all mesh samples follow more or less the same structure. In main.c, Bluetooth is enabled, and then mesh subsystem is initialized along with LEDs, buttons, and setting subsystem, and then the sample will start advertising unprovisioned node beacons. Since this is a server sample, it has few more things to look at. Let's see what is there in the model handler. As I mentioned before, BT mesh comp structure is populated in model handler.c module. In this structure, 4 instances of generic on-off server are instantiated on each element. But these instances are conditionally included depending on whether the given DK supports the LED or not. Since we are using Thingy 53, only first 3 instances will be instantiated in this sample when it is compiled. Along with generic on-off server, we have other mandatory foundation models like config server and health server present on them. Now, let's look at generic on-off server in a little bit of detail. On-off server instantiation requires the context, just like the client instantiation, and this context is held into a context array called as LED_context. Each on-off server instance in the context array requires a handler. In this sample, a same handler is used for all 4 instances. Now, let's see what is there in the on-off handlers. There are 2 types of handlers for this model, a get handler and a set handler. A get handler is called when generic on-off server receives a get message, and the set handler is called when generic on-off server receives a set message. Let's see what happens in the set handler first. In the set message, it receives 3 parameters, a value of the state on or off, and the transition parameters, the transition time and the delay. These parameters are processed by the set callback to create the transition. Since the generic on-off represents only a binary state of on or off, in this sample, there is no fading implemented. It simply models the effect of transition as described in the mesh model specification. If the current value of the state is different than the requested value, then the transition is started. Otherwise, it simply responds with a status message. The transition is started according to the specified transition time. When the transition starts, If the transition is from off to on, LED will be immediately turned on at the beginning of the transition. And if it is from on to off, LED will be turned off only when the transition completes. This is according to the binary state transition behavior as defined in the mesh model specification. Now let's see what happens when the get callback is received. When the get callback is received, the code fills up the value of the current state of the LED and also the remaining time for the transition, and provides these values through a status structure pointer. Generic on-off server then fills the provided value in the model message and sends the response. In order to have the correct implementation of mesh models as defined in the mesh model specification, it is mandatory to implement all the mandatory callbacks provided for a given server model. In case of generic on-off server, it is mandatory to implement get and set callback and model the transition behavior in the user application. Note that the transition behavior is on purpose modeled in the user application because you can implement the transition using the external LED drivers. Since the samples are provided for use on Nordic DKs, they implement the transitions on LEDs. However, you can use your own code to implement these transitions on other external hardware. To do so, you can use several things such as SPI interfaces or I2C interfaces to communicate with the external LED drivers and model the transition effect. Model interfaces are implemented in SDK and the transition behavior resides in the application. As long as you use the provided callbacks and implement the transition behavior, you can comply with the mesh model specification. Simply respond to a get by fetching the current value of LED or light state and respond to a set by writing given value of the LED or the light state. If the transition is specified, model the transition in the application. All right, so that concludes the code walkthrough for the light sample and the light switch sample. Now we will build these samples and flash them on the Thingy 53s and 53DKs and see a mini network demonstration. Throughout the demonstration, we will be learning additional concepts related to mesh networking. Let's understand how the demo is structured. We will be using one 53DK for the light switch sample. This DK has 4 push buttons. They will act like 4 individual switches. Additionally, we will be using 4 Thingy 53s and they will act as light bulbs. We will group them into 3 groups. First 2 thingies will be grouped into one group. The second set of thingies will be grouped into another group, and then there will be a third group that will comprise all these thingies together. What does the grouping mean and how it is going to work? We will get to those details in short while. Additionally, we will also show you how to configure the mesh network using NRF Mesh mobile app. Now let's see how to build and flash the samples on respective DKs. Before we build the application, we should increase size of the BTRX stack for NRF 53. In future versions of NRF Connect SDK, you won't have to do this, and this will be included as a default configuration. We have increased the stack size to 2200, and we will save this to project.conf file. I'm also going to update the number of subscriptions that are available per model. What is that? We will get to that during the demonstration. So Bluetooth mesh, number of subscriptions per model, we are going to set this to value 2. All right, now let's build the application. Okay, so now our application is built and we will flash it. To flash the application to Thingy, I have connected Thingy 53 to 53DK using a patch cable. In the NRF Connect SDK extension, I will click on the flash selected device, erase and flash to the board. I'm going to repeat the same procedure on the remaining 3 Thingy 53s and flash the light application to them. Okay, now let's add the light switch application. The light switch application will be flashing onto NRF 53DK and not on the Thingy. So we will select configuration for 53DK. We will use the project.conf as the default config. We won't build the sample and generate the configuration. Okay, now we have the configuration. In case of light switch sample, BTRX stack size is high enough and we don't have to change that one. Alright, now let's build the sample. This is going to take a while. Okay, now I'm going to disconnect the Thingy53 from DK so that we can flash the sample to DK. We will do full erase and flash. Alright, now we are set for the demo. Okay, now let's provision devices one by one. But before we do that, we should add application key to the NRF Mesh mobile app. For that, I'm going to go to the settings menu, click on the application key and add one app key. What is this application key? Let's take a look at how security is organized in the mesh network. Mesh network uses two levels of encryption, one at the network layer using network key and another using app key or the device key. An app key is always associated with one net key, and one model instance can be bound to several app keys, and some models are explicitly bound to the device key. This device key is generated at the time of provisioning by the provisioner and by the device, and it is unique for every device. This device key is never exchanged over the air. Application keys, on the other hand, are provided by the provisioner to the devices in the network after the provisioning is completed during the configuration stage. And these keys should be bound to a specific network key and to a specific model. Keys and key bindings can be used to give access privileges to the users. For example, one set of application or network keys can be given to installers and managers to enable access to all devices and all functionalities on those devices, whereas another set of application or network keys can be given to guest users to access only specific devices or functionalities on the devices. Okay, now let's see what is meant by binding a key. Binding a key is an ability to decrypt an incoming message with a given key and optionally send a response message. A model must be bound to a key to be able to communicate with one another. Models can also publish messages, and to do that, a publish key should be specified. This is associated with ability to generate outgoing messages encrypted with a given key. Both sender and receivers should have the correct configuration of the keys. If sending model sends or publishes a message using certain key, the receiver model shall be bound to the same key. Otherwise, the communication won't work. Now, let's get back to our demo. I'm going to scan for the devices, and I'm going to identify them. Okay, this is the third device, not the one we want. We want to provision the first device. And we found the first device. I'm going to click provision and choose no OOB. Okay, provisioning has been completed. All right, now let's see what do we see on the screen. We see the composition of device. The device has three elements. First element contains three models. As we have seen during the walkthrough of the light example, it contains configuration server, health server, and generic on-off server. The second and third element contains an instance of generic on-off server. For the purpose of this demonstration, we'll use generic on-off server on the element number 1. As you can see here, this element has a unicast address of 3. This unicast address is provided by the provisioner during the provisioning process. We should take this opportunity to quickly discuss the addressing scheme in the mesh network. There are 4 types of addresses in the mesh network: unassigned address, unicast address, virtual address, and the group address. Unassigned address, as the name suggests, is never used for anything. The unicast address is allocated to the device during provisioning. Provisioner only supplies address of the primary element. For other elements, a sequential address starting from the address of the primary element is assigned automatically by the device. In a mesh network, maximum of 32,767 addresses are possible. The third type of address is a virtual address. It represents a 128-bit label UUID. It is inefficient to use this address for configuration messages, for publication and subscription settings, because they become longer. Group addresses are most commonly used multicast addresses. They range from C000 to FEFF. There is also a special kind of group addresses called as fixed group addresses. These group addresses have certain functionality associated with them. A broadcast group address can be used to address primary elements of all nodes in a network. Similarly, all relays, all friends, or all proxies group addresses can be used to address primary element of those nodes which have the specific functionality enabled on them. Let's see how these addresses are used in practice. The addresses are used to send the messages from one node to another. When light switch wants to send a message to turn on the light at address 5, it generates a message and specifies the destination address as number 5. When the message is received by the neighboring node, which is also acting as a relay, it checks whether that address belongs to itself, and if not, it forwards the message. This way, message reaches to the destination node by propagating over the network via multiple hops. Unicast addressing is used for one-to-one communication. Multicast addressing is used for one-to-many communication, and it helps in establishing publish-subscribe paradigm. This is an important concept for the mesh networking. Sender model publishes to a specific address, and receiver model can subscribe to that specific address. This helps in the maintaining a mesh network in a sense that if one device fails and needs to be replaced by another device, only the publish or subscription configuration of that device needs to be updated. Rest of the network can continue to operate on its own as configured before. Now we will also talk about the model subscription. A model can subscribe to group or virtual address, and model cannot subscribe to a unicast address because sender model can publish a message directly to the unicast address. We will also look at the model publication. Model publication can be configured for unicast, group, or virtual addresses. When the model publication is configured, a model can publish a message to a given address. A message can be published periodically, or it can be published aperiodically when external stimulus is received, such as when user presses a button. And if this publication is configured for unassigned address, then the publication gets disabled. During the publication configuration, several parameters are specified. For example, publish address, period, app key index, friendship credential, TTL, retransmit count, and retransmit interval steps. In today's demo, we will not use all of these parameters. Instead, we will use only publish address and app key index parameters. Okay, now let's continue configuring our recently provisioned node. I'm going to configure the generic on-off server on first node that we just provisioned. The configuration would include doing subscriptions as well. So to do that, first let's define the group addresses. I'm going to click on the groups icon on the bottom portion of the screen and add one group. Let's name this as group A. Then I'm going to add another group, group B. And then another one called as group C. I'm going to leave the group addresses as specified by default. Now I'm going back to the network and the node configuration, opening the generic on-off server instance. And first thing I'm going to do is to bind the application key to this model. Now, to bind the application key, a device needs to be added with an application key first. We added the application key to the mobile app, but we haven't yet sent it to the device. On this screen, we will add that application key to the device. Okay, and we will bind that application key to the generic on-off server. Now, in this demonstration, we are not going to use publication on the generic on-off server, but instead, we are going to subscribe it to the two groups. As shown in the demonstration slide, we have three total groups. Thingy first and second are subscribed to group A, third and fourth one are subscribed to group B, and all of them are subscribed to group C. So since we are configuring the first thingy, I'm going to add it to group A and to group C. Okay, now I'm also adding this thingy to group C. All right, the configuration of first thingy is complete. Now we are going to add the second thingy to this network. Okay, that's the fourth one. That's the third one. So the last one must be the second one. Yes, I'm going to provision it without any out-of-band authentication. And I'm going to follow the same steps. I'm going to add the application key and then bind this application key to generic on-off server on element 1. Then I'm going to subscribe this thingy to group A and to group C. Similarly, I'm going to provision thingy 3 and 4. This is the third one. For thingy 3, I'm going to add it to the group B and group C. Now I'm going to provision the last remaining thingy. All right, so the configuration of all the thingies is complete. So now we have 4 lights in our mesh network. The next step would be to provision the switch. We have 53 DK acting as a light switch. This DK has 4 push buttons, and these buttons will act as 4 individual switches. Let's add the light switch to the mesh network. Okay, now as I mentioned before, since the light switch should communicate with all these lights, the light switch must also have the same application key. I'm going to add the same application key to this device, and then I'm going to bind this application key to all the generic on-off client instances on this device. As we have seen in the sample walkthrough, this device has 4 elements. First element has config server, health server, because they're mandatory, and a generic on-off client. And other 3 elements have 1 instance of generic on-off client. So let's start configuring this generic on-off client. I would like to take your attention back to the presentation slide for a reference. The first switch is going to talk to thingy 53, first one. So the first thing I should be doing is to bind the application key to this model and then set a publication to a destination for thingy 53. So that's the first one in this list. First button should be configured to communicate with the first thingy. Now I'm going to configure the second push button or the generic on-off client instance associated with the second button to communicate to group A, the third one to communicate with group B, and the fourth one to communicate with group C. Let's quickly check if our configuration of first button has actually worked as expected. So I'm going to press button 1 and the thingy 1 turns on. And now it turns off. Great. So now I'm going to configure button 2 to communicate with group A. So I'm opening generic on of client instance, binding the application key, and setting the publication to group A. All right. Similarly, I'm going to set publication for the third button to group B. And then I'm going to configure the publication settings for the fourth instance to talk to group C, which addresses all 4 lights. All right, so now we have the complete mesh networks set up. We have 4 lights and a switch. We have configured first button to talk to the first light. So this works as expected. And we have configured the second button to publish to group A. This also works as expected. We have configured third button to talk to group B. That works as expected. And we have configured the fourth button to talk to group C, which is basically all the thingies. And that's the mesh networking demo. You can find more mesh samples in the RF Connect SDK. You can browse them and explore them. SDK provides all models from the Bluetooth mesh model specification. It also provides Silver and Ocean vendor model and lots of samples for evaluation. The mesh implementation in RF Connect SDK is also fully qualified for use in end products.
Okay, thank you for your presentation, Umkai. It looks like we have quite a few questions to answer. So,
All right. Yeah, I changed my audio setup a bit. I hope you can hear me. Let's see what are the questions. Okay, I'm going to paraphrase the question. Okay, so here is the question from JP. Whether one should be using an RF5 SDK for mesh version 5.0. Well, it is not recommended to use an RF5 SDK for mesh version 5.0.0 for any new products. It is strongly advised to move to an RF Connect SDK since that is the supported SDK now from the Nordic for all of the Bluetooth and mesh development. The new SDK has all the lighting examples and all the models from the mesh model specification, and it's qualified as mentioned a few moments before.
Then there's a question if it's possible to get team support from our end beyond the dev zone, and also if it's possible to get connected with field application engineers specializing in Bluetooth mesh. So we prefer that most support goes through dev zone. It's actually quite responsive, and we try to provide answers or responses within next business day to all requests. We also have some partners that can help with development. I will share in the chat a link to our webpage listing those partners. Also, it's possible to contact our sales teams through the regional sales directors. If you don't know how to do that, you can also ask how to do so on the dev zone.
Okay, so the next one is a question about synchronization. What to do if one wants to synchronize network to one master node? How would you recommend to implement this? That's the question. Well, here I assume that synchronization means time synchronization. If that's the case, you could use time models available in the mesh model specification. Time models allow various nodes to propagate the time and let the whole network synchronize to the time authority.
There is a question about what devices can use this mesh technology. Specifically, can Bluetooth mesh be used on NRF 52832? Answer is yes. And does it have any limitations compared to newer chips? So it comes down to what peripherals and what memory constraints you have for your application. For the NRF 52832, it might be a good idea to go for the bigger variant with the 512 kilobyte of flash as opposed to the smaller one. But apart from that, it's the stack is qualified on NRF 52832, 833, 840, and also the NRF 5340.
Okay, then let's see what we have here. Next one. Can you provide some idea about battery consumption for mesh use compared to the star use? Okay. Um, if you use LPN feature in mesh profile specification, you can get um, fairly low operating current, going to few microamps or few tens of microamps, I would say. And the star use case which you are talking about here is, I assume, the GATT connection based. For the general mesh node, like the one which is acting as a relay or always on light bulb or always on mesh node which is acting as an edge node, it will be the power consumption will almost be equal to the full power consumption when the CPU is active. Of course, it will depend what else is happening in your user application which keeps the CPU awake all the time.
Then there's a question, how can I determine the worst case latency of a mesh network? For example, if I assume that nodes are spaced 10 meters apart and messages are only allowed to be repeated once, what worst case latency could be expected? And could we meet the 10 millisecond worst case latency requirement in this setup? 10 milliseconds is very short. The average in a Bluetooth mesh network would be somewhere between 15 and 25 milliseconds per jump with a long tail. We have seen up towards 125 millisecond worst case in the long tail per hop. So you would probably look into other technologies like connection-oriented technologies for the 10 milliseconds latencies. Is it possible to transfer the CDB, the configuration database, from the initial provisioning device to another device or provisioner? Yes. So actually, in the Bluetooth specification, it's specified that you should be able to do so, although the method for actually transferring this database is out of scope. But for instance, with the NRF Mesh app, you can export the configuration database as a JSON file and import it to a different smartphone with the NRF Mesh app. And this JSON format is also specified by the Bluetooth SIG.
The next one is there a way to automatically reconfigure a device if it fails and loses its configuration? Could this be via the device GUID/device ID? First of all, a device will not lose its configuration automatically unless it malfunctions, and in that case, it won't be able to be reprovisioned. If the provisioning fails for some reason, then the device won't get provisioned and it will always be brought up as an unprovisioned device. So in that case, you can retry the provisioning again. And the reprovisioning will happen just like the way you do the provisioning of the device for the first time. Device will start advertising unprovisioned device beacon. This provisioner will have to scan for it and provision the device. The next one is about sniffing. If mesh messages are encrypted, can we observe those messages with sniffer tools? Yes, that's possible. If you use some of the leading Bluetooth sniffing tools available on the market, they can parse the mesh traffic. They will need to be provided with the keys used in the mesh network though. So you will have to either print the keys for the device, especially the device key and the network key, by using debug logs in your application, and then provide these keys to the tool. After that, tool can analyze the traffic and give you a rich message sequencing and flow.
Where the nodes are distributed at long range, for instance, across a city or a campus, does mesh support long range? No. So Bluetooth mesh is built on Bluetooth 4. So that was before long range. So no, that's not possible in Bluetooth mesh.
Then I have a follow-up question to that question. Can you use the NRF 21540 RF FEM range extender with the Bluetooth mesh?
Yes, I believe so.
Yes, you can use the range extender with the Bluetooth mesh, and basically you can use range extender with any Nordic chip, and whatever protocol you run on it, including mesh, will benefit from it.
So maybe that's the solution for that person.
Yes.
Okay, I think we got through all the questions. If there's no last-minute questions coming in right now, I will call this webinar and end it. There's been some questions about when the slides will be available and when the recording will be available. I'll try to get them out tomorrow. At least they will be available before this time Friday. If you want to register for upcoming Nordic Tech webinars, or if you want to access the recording of this webinar or the slides from this webinar, you can go to webinars.nordicsemi.com. Thank you all for watching and have a wonderful day.